In this lecture, we're going to continue our discussion of rational functions. We're going to focus on graphing, but at the end we'll talk a little bit about asymptotes that aren't horizontal or vertical. Here's a set of suggested steps for graphing a rational function. First thing I would do is find the asymptotes. I would use dashed lines to indicate where those asymptotes are, and for any vertical asymptotes I might consider finding the behavior on each side. It's always nice to have a couple of points on the graph, so I would find the y-intercept if it has one. If the function is not defined at 0, there might be a hole in the graph or an asymptote there. But if you can plug 0 in for x, I would do that and figure out where the y-intercept is. I'd find any x-intercepts if it has any, and if it's easy to do. You find the x-intercepts by setting the numerator of the rational function equal to 0. And if that's going to give you a complicated equation, then I wouldn't even bother. I'd just find some other points. But if it's easy to find the zeros of the numerator, then I would do that because that's a couple of simple locations. If there are any holes in the graph, I would figure out the locations of those. And after those first 4 steps, I'd stop and see what information I've gathered, look at my graph, and see if I have a pretty good idea of what's going on. If I do, if there's some interval of x values where I'm not really sure what the shape of the graph would look like, then I might plot some points on there, or I might use a sign chart to at least figure out if the function is positive or negative on that interval. And then I'd sketch the graph. Let's put this into action. Let's sketch the graph of the function f of x equals 2x plus 4 over x minus 3. The first thing I would do is find the asymptotes. I can see that the numerator and denominator have the same degree, and so this function is going to have a horizontal asymptote. I find the ratio of the leading coefficient. The leading coefficient of the numerator is 2, the leading coefficient of the denominator is 1, and 2 divided by 1 is 2. Now that is not the horizontal asymptote, that's just the work that I did. The horizontal asymptote is the line y equals 2. Y equals 2 is a horizontal line that passes through all the points whose y-coordinate is 2. And I mentioned this in the previous video. When I find a horizontal asymptote, I only mark it on the ends to remind myself that that's the end behavior. But feel free to draw that dashed line all the way through. A lot of textbooks will do that. There's nothing wrong with dashing it all the way through. Next, I'm going to look for any vertical asymptotes, and to find vertical asymptotes, I need to have this factored to make sure that there's no cancellations. So I'm going to factor the numerator to 2 times x plus 2. That's over a denominator of x minus 3. I see that no factors cancel, and so any zeros of the denominator will correspond to vertical asymptotes. The one number that makes the denominator 0 is 3. Again, the vertical asymptote is a line, so make sure you write its equation, x equals 3. Now that we've found the vertical asymptote, I suggest that you find the behavior on each side of the asymptote. This isn't an absolutely necessary step because sometimes you get this information for free by doing the other steps. But let me show you what I mean by determining the behavior. I'm going to ask what happens to the function as x approaches 3 from the left, and I'm also going to figure out what happens as x approaches 3 from the right, both sides of the asymptote. If we approach 3 from the left, then we're plugging a number that's ever so slightly smaller than 3 into the function. If we plug a number smaller than 3 into the numerator, we're definitely going to get a positive result. And if we plug a number smaller than 3 into the denominator, we get a negative result. And so the quotients just to the left of 3 are going to be negative. And because those quotients are negative and we're approaching an asymptote, we know the behavior has to be to shoot towards negative infinity. As a rational function approaches one of its vertical asymptotes, it either shoots down towards negative infinity or up towards positive infinity. We've determined that on the left side of 3, just barely to the left of 3, the quotients are going to be negative, so the function has to be shooting down towards negative infinity. On the right side of 3, the inputs will be ever so slightly larger than 3. The numerator will still be positive. If you plug a number bigger than 3 into the numerator, you're going to get a positive result. The denominator will also be positive, because when you take a number bigger than 3 minus 3, you get a positive result. Because the outputs are positive and unbounded in magnitude, this function must be going towards positive infinity on the right side. So like this. Once you've found the asymptotes and determined the behavior on each side of the vertical asymptotes, I would find the intercepts, if they exist. Here we're not going to have any issues. To find the y-intercept, we plug 0 in for x. In function notation, we can just write that as f of 0. That's 2 times 0 plus 4 divided by 0 minus 3. That's negative 4/3. Negative 4/3 is just a little bit smaller than negative 1, so the point will be right here. Then I would find the x-intercept if it's easy. To find the x-intercept, you take the reduced version of the function and set its numerator equal to 0. Now this function didn't reduce at all, so it doesn't matter whether we set 2 times x plus 4 equal to 0 or 2 times the quantity x plus 2 equal to 0. It's the same thing. I'll take the original numerator. 2x plus 4 equals 0. Subtract 4 from both sides, I get 2x equals negative 4. Divide both sides by 2, I get x equals negative 2. And that's a point at negative 2, 0. And from those 2 points alone, we have a pretty good idea of what the left side looks like. So the function bends into the asymptote like this, comes through these 2 points, but notice that on the right side of the asymptote, we didn't come up with any points. Without this behavior, we wouldn't really know what the function is doing. We would have had to plot some points, and that is an option I put into my list. If necessary, you can plot some more points or make a sign chart to figure out where the function is, but because we took the time to determine the behavior on each side of the vertical asymptote, we also know what's happening up here. The function's going to bend down towards the asymptote like this, and there's a pretty decent sketch of what that graph looks like. The only issue that we didn't address is whether or not this function actually touches its horizontal asymptote. And to determine that, you set the function equal to the y-coordinate of every point on the horizontal asymptote. So in this case, we would set 2x plus 4 over x minus 3 equal to 2 and try to solve for x. In this example, you don't get any solutions, and so the function doesn't touch its horizontal asymptote. If you do get a solution, then that's just one more point on the graph that you can plot. Let's do another example. Let's sketch the graph of f of x equals 32x over x squared minus 16. I would start by finding any asymptotes. I notice that the degree of the numerator is smaller than the degree of the denominator, and so the horizontal asymptote is automatically the line y equals 0, the x-axis. Then I would find any vertical asymptotes, and I find those by getting the function factored and then looking for zeros of the denominator. The denominator is a difference of squares, so it factors to x plus 4x minus 4. There are no cancellations here, and so we get 2 vertical asymptotes, x equals negative 4 and x equals 4. In the last example, I found the behavior on each side of the asymptote, so this time I'll show you an alternative, which is just to plot some points, if we need them. It is a good idea to find the behavior on each side of both asymptotes here, but I want to show you an alternative method, which is to plot some points, so that's what I'm going to do in this example. Now that I've got the vertical asymptote, I'm going to look for any intercept. You find the y-intercept by plugging 0 in for x. If you can. Sometimes you're not allowed to plug 0 in for x, but we already know the domain restrictions are negative 4 and 4, so we're okay here. That's 32 times 0 over 0 squared minus 16. Well, the numerator is 0 and the denominator isn't, so this comes out to 0. So we get the point 0, 0, and notice that that is a point on the horizontal asymptote. This function actually crosses through its horizontal asymptote. Functions can touch their horizontal asymptotes, they cannot touch the vertical asymptotes. When I go to find the x-intercept in this example, I get no more information. When I set the numerator equal to 0, well, that just has the solution x equals 0, which is the point that we've already found. So we only have this one point. We don't have a whole lot to go on. If we had found the behavior on each side of the vertical asymptotes, we'd be good to go. But the other option is to just find some points on each of the intervals that you don't know a lot about. This is equivalent to making a sign chart. So I'm just going to plug some numbers in for x and figure out where these points are. For example, I have no idea what's going on to the left of negative 4, so I might evaluate f of negative 5 just to give me an idea. F of negative 5 would be 32 times negative 5 over negative 5 squared minus 16. That's negative 160 divided by 25 minus 16, which is 9. Now I can't actually plot this point, but I know that it's somewhere down here, and that tells the story of what's going on. The graph must be shooting down towards negative infinity at the vertical asymptote, and then bending into the horizontal asymptote like this. I know it doesn't cross the horizontal asymptote because I've already found the only point on the x-axis. Notice that what I did here is equivalent to just making a sign chart. I didn't actually plot this point, I just figured out that the function was negative at that point and then drew that piece of the graph accordingly. I'm going to have to do this a few more times because I also don't know what's going on, say, between negative 4 and 0, so I might plug in negative 1. f of negative 1 is 32 times negative 1 over negative 1 squared minus 16. That's negative 32 divided by 1 minus 16 is negative 15. And that's a little bit bigger than 2. Well, now I know what this part of the graph is doing. I know it doesn't bend back down because there aren't any more x-intercepts. So the function must go through this point and up towards positive infinity like this. Kind of missed that point. Let me just draw on top of it. Now I need to figure out what's going on the other side between 0 and 4. So I'm going to plug in positive 1. Let me be lazy here. Well, that's just going to be positive 32 divided by negative 15, which is a little bit smaller than negative 2. Be down here. The function can't bend back up because there aren't any more x-intercepts, so it must shoot down like this. And now I need to know what's going on the right side of the second asymptote. I could plug in 5 for that. Again, let me be lazy here. So 5, 5, 5. 32 times 5 is positive 160. The denominator is going to be positive 9. That output's going to be somewhere close to positive 18, so it's way up here. We know that the graph levels off at the asymptote without crossing it, and so the function will look something like this. If we had found the behavior on each side of the vertical asymptotes, we would have figured out the exact same graph. You have to decide whether you think it's going to be easier to plot some points, or if it's going to be easier to determine the behavior like we did in the previous example. As an aside, if we had taken the time to notice that this function is odd, we could have tested this to see if it was odd. Then we could have just drawn these first two parts of the graph and then drawn the reflections through the origin to get the rest of the graph. That might have been helpful. It's not something that I typically do as part of my procedure, but if you notice that the function is even or odd, using that symmetry is often handy. Let's try another one. It says sketch the graph of f of x equals 1 minus x squared over x squared plus x. So I like to look for the asymptotes first. I notice that the degree of the numerator and the degree of the denominator are the same, and so I find the horizontal asymptote by taking the ratio of the leading coefficients. That's negative 1 divided by 1. The horizontal asymptote is the line y equals negative 1. Down here I'm going to draw some dashes to indicate that the function should level off there on the ends. To find the vertical asymptote, I need to get the function factored. The numerator factors to 1 minus x times 1 plus x. In the denominator I can factor this to x times x plus 1. 1 plus x and x plus 1 are the same factor, those cancel. And so this reduces to 1 minus x over x. The vertical asymptotes correspond to any zeros of the denominator in the reduced version. So while there are two numbers that we're not allowed to plug in for x in this function, there's only one that corresponds to a vertical asymptote, and that's x equals 0, which is the y-axis. The other domain restriction is going to correspond to a hole, and I'll get to that in a little bit. Now I'm going to find any intercepts. To find any y-intercepts, you plug 0 in for x, but we just said that 0 is not an allowable input. F of 0 is undefined. So this function doesn't have a y-intercept. To find any x-intercepts, you want to set the numerator of the reduced version equal to 0. Well, if 1 minus x is equal to 0, then x equals 1. That point's right there. And based on that one point, I have a pretty good idea of what's happening on the right side of the graph. It's going to bend through like this. I don't really know what's going on the other side, but remember that there's a hole in the graph. Maybe that'll give us some information. The hole in the graph has an x-coordinate of negative 1, because we're not allowed to plug negative 1 into the original function. To find the y-coordinate of the hole, you plug its x-coordinate into the reduced version. If I plug negative 1 into the reduced version, the numerator is 2 and the denominator is negative 1. That's a y-coordinate of negative 2. So at negative 1, negative 2, there's a hole in the graph. And I'm pretty sure I know what the graph looks like from here. The function's got to bend like this and level off at the asymptote. And down here the function has to go through that hole and bend away. It can't bend up because there are no more x-intercepts. Let's do one more graphing example with an issue that we haven't addressed yet. This says sketch the graph of f of x equals 12 over x squared plus 4. Horizontal asymptote's easy to find. The degree of the numerator is smaller than the degree of the denominator, and so the horizontal asymptote is the line y equals 0, that's the x-axis. Now we'll try to find the vertical asymptotes, and here's the weird part about this one. This function doesn't have any vertical asymptotes. We can't get the denominator factored using integers, and even if we take the time to set up the equation, x squared plus 4 equals 0, when you go to solve that, you don't get any real solutions. If there are no real solutions, then we can't have any vertical asymptotes in the graph. So there are no vertical asymptotes. With no vertical asymptotes, this graph's going to look a little bit different, and we're probably going to have to spend time plotting points because that's the only way we're going to get information. One point that we like to find is the y-intercept. You get that by plugging 0 in for x. So we get 12 over 0 squared plus 4, which is 3. So this graph goes through the point 0, 3. Next we try to find the x-intercept, but there aren't any. The numerator is a constant. It will never be equal to 0. There is no input that will make the numerator 0 because the numerator is constant. The numerator will always be 12. So this is really all we have to go on so far. So we'll probably want to plot a couple of points. Like let's plug in, let's say, -2. F of -2 would be 12 over -2 squared plus 4. That's 12 over 8. Which reduces to 3 halves, or 1.5. So at -2, the output is 1.5. Now I have a pretty good idea what the left side of the graph looks like, because remember, the function will not touch the x-axis. There aren't any x-intercepts. So the function's going to bend into the asymptote like this, come up and get this point. From here we could do something super nerdy and show that this function is even and therefore it's symmetric through the y-axis. I'll be a little more basic and just plot another point, but I'll plug in 2 to show you that symmetry. If we plug 2 into the function, we also get 12 over 8, which reduces to 3 halves. Again, we get this point at 2 comma positive 3 halves, and the function is again going to bend in towards the axis like this. So we get this symmetric graph. To end this video, we're going to clear up some loose ends from the previous video. We talked about the rules for finding horizontal asymptotes, and we said when the degree of the numerator was equal to the degree of the denominator, you get a horizontal asymptote, and when the degree of the numerator is smaller than the degree of the denominator, you get a horizontal asymptote. But we didn't cover the case where the degree of the numerator is bigger than the degree of the denominator, and that's because you don't get a horizontal asymptote in that case. You either get an oblique or a curvilinear asymptote. Here's the rule. Let f of x equal g of x over h of x. If the degree of g of x is greater than the degree of h of x, then the graph of f of x has an asymptote of the form y equals q of x, where q of x is the quotient obtained when dividing g of x by h of x. Now it turns out this rule also works for horizontal asymptotes, but we kind of have those shortcuts that we talked about before. We don't have to do the division. But when the degree of the numerator is bigger than the degree of the denominator, we have to divide in order to find what the asymptote is. Let's do an example of this, and in this first example we're going to get an oblique or a slanted asymptote. Let's find the oblique asymptote of the graph of f of x equals x squared minus 5x plus 4 divided by x minus 2. You can tell that this graph isn't going to have a horizontal asymptote because the degree of the numerator is bigger than the degree of the denominator. The way that you can tell that this is going to be an oblique asymptote is because the degree of the numerator is 1 bigger than the degree of the denominator. So the asymptote is going to be a slanted line. And how do you figure out what line that is? You actually divide the denominator into the numerator. You could do that same thing to find horizontal asymptotes, but it's usually just easier to follow our shortcut rules. We can do this division in this example either by using long division or synthetic division. I prefer synthetic division, so that's the way I'm going to do it. I'm going to put a 2 into the nook. I'm going to write down the coefficients of the numerator, and I'm going to divide. Bring the 1 straight down. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. And we get a remainder of negative 2, but that actually doesn't matter. We figure out the asymptote by looking at the quotient that you get. It's y equals the quotient. So the quotient in this example is x minus 3. That means that the oblique asymptote, which I'm going to denote by OA, is the line y equals x minus 3. So this graph doesn't have a horizontal asymptote, it has an oblique or slanted asymptote. And let me show you that in the graph. We haven't seen one of these as a class, so let me show you what I mean. I've got the function in y1 here, and if I graph this on the standard window, you'll notice that the function doesn't level off horizontally on its ends, it becomes slanted. And it's hard to tell exactly where that goes through, but there's this line that passes right through here, We're claiming that line is y equals x minus 3, and that's hard to verify from the graph, but we can do this with the table. I'm going to access the table, and what I'm going to do is plug in some numbers with really big magnitudes. If our asymptote is right, then the outputs of this function should come close to the outputs of the asymptote. So for instance, when I plug in 10, the output should be close to 10 minus 3, which is 7. And it's not that far off. If I plug in 100, the output should be close to 100 minus 3, which is 97. It's really close. If I plug in 1,000, it should be close to 997. It says it's equal to 997, but if we go to it, you can see it's actually rounded. But it's really, really close. This function is leveling off at y equals x minus 3. The same thing should happen for negative inputs. Let me clear these. So if I plug in negative 17, the output should be really close to negative 20. If I plug in negative 100, the output should be really close to negative 103. And it says it's equal to 103 at first glance, but you can see it's been rounded. This is one practical use of asymptotes, by the way. Suppose somebody told you to plug negative 10,000 into this function. Rather than actually taking the time to plug negative 10,000 in for x and try to simplify it, you can be like, it's going to be close to negative 10,003. And again, it's not actually equal to negative 10,003, but wow, is it close. So we can see numerically that our oblique asymptote is almost certainly right. Let's do another example, and this time we're going to find a curvilinear asymptote. You get a curvilinear asymptote when the difference in the degree of the numerator and the degree of the denominator is 2 or more. Like here, the degree of the numerator is 3, and the degree of the denominator is 1. And so the asymptote isn't going to follow a line, it's going to follow a parabola, because the difference is 2. Let's figure out which parabola it follows. The way we do that is we divide the denominator into the numerator. Once again, synthetic division is an option, so that's how I'm going to do this. I'm going to put a 1 into the nook. I'm going to copy down the coefficients of the numerator. The 1 comes down. 1 times 1 is 1. Negative 1 plus 1 is 0. 1 times 0 is 0. 3 plus 0 is 3. 1 times 3 is 3, and negative 7 plus 3 is negative 4. That last part isn't actually necessary for what we're trying to do, because all we need is the quotient. The remainder doesn't matter when you're trying to find an asymptote. So the quotient is x squared plus 3. Remember that this is x squared, this is x, and this is the constant term. So our curvilinear asymptote is y equals x squared plus 3. It follows a parabola. So let's look at what the graph of this function looks like. And to be honest with you, I had to play with the window settings quite a bit to get a decent graph of this. You won't get a decent graph of this from the standard window. But I've played with the window settings a little bit so that we can see that the function doesn't level off at a line, but on some curve on both sides. There's a break in the graph right here because there's a vertical asymptote at x equals 1. And then the function kind of bends off on the left side and on the right side. It's hard to tell that that's y equals x squared plus 3, but you could again investigate that numerically. I'm not going to walk you through that again. So we've gone through some examples of finding graphs of rational functions by hand. We found oblique and curvilinear asymptotes. If you have questions about our procedure for graphing or our method for finding these weirdo asymptotes, don't be afraid to contact me. You can shoot me an email or see me in an office hour.